Okay, this is C2 revision. We're going to make a start going through the units, and we're going to start with Unit 1. So, structure and bonding. Compounds are substances in which two or more elements are chemically combined together. So here you can see a compound, you see water, H2O, and it's made up of two atoms, two different types of atom or element, oxygen and hydrogen. If you look at the outer circle, you can see that oxygen has 6 dots in its outer shell because it's in group 6, and hydrogen has 1 cross because it's in group 1. In terms of them getting a full outer shell, elements must bond or join together. In this case, they've joined covalently. So you can also do ionic bonding, and that's what you can see here. So ions are formed when atoms transfer electrons. So on the outer side, you can see sodium in grey and chlorine in green. Okay, and what you can see there is that the sodium, the outer shell electron, if you look at the middle diagram now, the sodium has 1 electron in its outermost shell. And you can see the red arrow is showing that that electron is moving to chlorine. Chlorine has 7 in its outer shell. So by sodium losing that 1 in the outer shell, it goes down to its next full outer shell and is very happy. And chlorine steals that 1 from sodium and makes its outer shell up to 8. Okay, so when they lose electrons that are negative, they become positive. So sodium becomes a plus, and chlorine has gained that negative electron, so it's become negative overall, so it's Cl minus. And you can see there on the outer diagrams, Na plus and Cl minus. So when we talk about ionic bonding, what we talk about now is an attraction between a positive and negative ion. So a sodium ion here you can see is positive, which we just looked at previously, and the chlorine is negative. So if you look at the outer shell electrons, sodium has lost that 1, it's gone to its next outer shell, and that 1 red dot is now featuring on chlorine on the outer shell electron, so that's now formed sodium chloride. If you look down underneath that, you can see magnesium ion, and you can see that the magnesium would have had 2 in the outer shell, which is given to oxygen, because oxygen is in group 6, it's got 6 crosses in its outer shell, plus those 2 from magnesium, which take it to 8 in total. Okay, so it can only get 2 in the first shell, and then it wants 8. So if there's a positive and a negative ion, which is what you can see here, there is what's called an electrostatic force of attraction between those 2 ions. Okay, so group 1 then, which we've looked at, have 1 electron in their outer shell. Remember, you have your periodic table in the exam, so you can use it to identify all of your ions, okay? So with lithium, for example, in group 1, it's 1 electron goes to any other non-metal, and in this case it's going to fluorine, which is in group 7. Fluorine will become negative, lithium was positive. Okay, so in comparison to that, things in group 7 have 7 in their outer shells. They're looking to steal just 1 more to fill the outer shell. So 1s and 2s actually combine really effectively together, so they give their 1 away. Now, when you may be asked to write ionic formula, and you can see this here, the ionic formula is in the final column. So MgO, NaCl or MgCl2. When you write a formula, don't want pluses and minuses in them. That's an ion. A formula should have no pluses and minuses. It might have some little 2s or 3s or 4s, but it won't have any plus and minuses. So if we look at the first row, we can see that magnesium has given its 2 to oxygen. So to make it balance, I only need 1 magnesium and 1 oxygen. So the formula becomes MgO. Sodium and chlorine, you can see the 1 from sodium in the outer shell goes over to chlorine. Chlorine goes up to 8. Sodium goes down to its next full shell. So we only need 1 sodium and 1 chlorine to make everyone happy. So it's NaCl. And if we look at the last row, we can see that magnesium is giving away 2, but each chlorine can only accept 1 more to make it 8. So in this case, I need 2 chlorines to take the 2 electrons from the outer shell of magnesium. So the formula there is MgCl2. Okay, again, remember that the middle column shows the ion charges. They are all on your data sheet. So if you don't know whether they go positive or negative, all you have to do is look at the numbers to work it out. There'll be a separate little video on writing ionic formula if that's helpful to you. Okay, so they can ionically bond, but they can also covalently bond, and that's what's happening here. There are very few you'll have to draw, so practice these. Also practice carbon dioxide as well and methane. Neither of these are shown here, but are worth practicing. So this is between, covalent bonding is between non-metals, and this is when they share electrons. So ionic was transferring electrons, covalent is all about sharing electrons. Covalent bonds are really, really strong. They're the strongest bonds we've got, so you really will struggle to break this bond using a high temperature to be incredibly hot. Looking at your outer shell electrons again, you need to try and work out how you can share the electrons to get a full outer shell. So if you look at hydrogen, the two H's first of all, they only have one electron in their outer shell each. So in this case, they share that electron in their outer shell, and they both effectively now have two. Chlorine has 7 in the outer shell, so just share 1 each, and therefore if you go around each shell, you can count 8 on each circle. Can you see on these diagrams clearly how there's a dot for one atom and a cross for another atom, and it's really obvious which are sharing, because you can see a clear overlap. Please make sure if you have to draw these in the exam, you have a very clear overlap between the atoms that you've got on your piece of paper. Okay, so again, go away and practice these, and if you need some help, there'll be a separate video on how to draw these out. Right, we can also describe covalent molecules as giant. In the second unit, we'll look at the properties of simple and giant covalent molecules. These are giant, and you can see that on the previous one, we only had 2 atoms, like 2 hydrogen atoms to make a hydrogen molecule, whereas on this one, you've got loads of atoms. All these little circles are all atoms. So the one in black is your diamond, and this is made up of carbon, and then the other one is silicon dioxide, made of silicon and oxygen. You don't have to draw these out, you just have to know they're examples of giant covalent molecules. Okay, you also need to know that metals consist of giant structures of atoms in regular pattern. You could have drawn this out if I asked you to draw a solid. In terms of atom structure, you would have seen at Key Stage 3. So you can just see that metals look like that, nice neat rows of atoms. If you're doing higher tier though, you do need to know that the bonding in metals, you need to go into that diagram in a little bit more detail. All we've shown here is the atom is a circle. Metals are in group 1, 2 or 3 of the periodic table. So what they do to get that outer shell that all atoms are aiming for, they lose those outer shell electrons and they share them. So you can see this grey square, this cloud of delocalized electrons. So they're sharing all that negative charge between them to try and achieve 8 electrons each in the outer shell. And because they've lost those negative electrons, the metal atom itself has now become positive. So we've now got negative electrons and positive ions, and that holds the whole metal together. Okay, and you can see here then in another diagram exactly the same thing, the positive metal atom and the free delocalized electrons floating around the outside. And what happens if these will conduct electricity and they will conduct heat? If you think about your physics, it's these little free electrons which will move and conduct electricity and conduct heat. And it's only metals which will show this sort of bonding. Okay, and again, like we saw with ionic bonding, because we've got a negative electron and a positive atom, we've got electrostatic forces of attraction holding them together. Okay, not as strong as covalent bonding, but certainly very strong force. Okay, let's go on to looking at properties then of the structures we've just talked about. So these are covalent molecules. They share electrons. You can see clearly they're sharing. These are called simple. They're very easy to draw, very small, maybe 2, 3, 4 atoms. And what happens is these have low melting and boiling points. So if we look at water in the middle there, water is made of 3 atoms, 2 hydrogen, 1 oxygen. When you boil water, it's relatively easy. They have a low boiling point. You are not breaking hydrogen and oxygen. You are just moving one water molecule a little bit further away from another water molecule. So you're breaking the force in between the water molecules. You're not breaking the covalent bond. At no point in your C2 exam should you talk about covalent bonds being broken, because you're not going to do that. You're going to break the force between simple molecules. So here you can see a diagram and you can see the simple molecules, and between them you can see these little dotted lines, okay? In between, if you look at the green and the grey diagram, there's a dotted line, and in the other diagram there's a blue arrow. Between covalent molecules you have an intermolecular force, okay? That's weak. If in the exam they ask you, why does something have a low melting or boiling point, you should use the word weak. So something has a low melting or boiling point, it has a weak force of attraction or a weak bond. If it has a high melting or boiling point, it has a high or strong bond or force of attraction. So properties of simple covalent molecules are they have a low boiling point and melting point because they have a weak intermolecular force of attraction between the molecules. Okay, you do not break the covalent bond, you overcome that weak intermolecular force of attraction. Okay, simple molecules don't conduct electricity because they have no charge. For electricity, if you think about a battery, it has a positive end and a negative end. So the molecule has to be positive or negative to go to one of those ends of the battery. If it doesn't have a charge, it's not moving, it's not going to conduct electricity. So simple molecules do not conduct electricity. You may think that's a little bit strange because you may look at it and see water. Water, pure water, will not conduct electricity. The water you have in your tap, though, is not pure. It contains loads of ions which are charged, which is why the water from your taps will conduct electricity. It's not because of the molecule, it's because of impurities within that water that you are drinking. Okay. Ionic molecules, and if we look at these in terms of property, we can see that they're described as a giant ionic lattice. Okay, they've got negative ions and positive ions all pulling together with that electrostatic force of attraction. Because of that, their forces are very, very strong. So ionic molecules, have a very high melting and boiling point because they have very strong forces of attraction. So you can see there your simple covalent molecules, low melting, low boiling point, weak forces of attraction, and with the high boiling points and high melting points, we have very strong electrostatic forces of attraction. Okay. When you melt or dissolve ionic compounds then, in complete contrast to covalent, they will conduct electricity because they're ions, they're charged. So therefore the ions can move, they will be attracted to the positive and they will be attracted to the negative, so they will conduct electricity. But importantly, they have to be in liquid, they have to be molten, they have to move. A solid ionic compound like salt would not conduct electricity because it can't move. Salt can't move from one end to the other. Okay, so here you can see a diagram then. So if we look at A, it's distilled water. That means it's pure water. It does not conduct electricity. In the middle, you've got ions, but it's a solid. So again, it's not conducting electricity. It's not lighting up the bulb. And in C, you can see you've got positive and negative ions, which can move freely and conduct electricity, and therefore the light bulb is on in diagram C. Okay, atoms that share electrons can also form giant structures then called macromolecules, like we've already looked at in the unit 1. This is diamond and silicon dioxide. These are examples of giant covalent structures. These are incredibly strong. There are no intermolecular forces of attraction here. Every line you see on that diagram is a covalent bond, which means it's going to have a high melting point or boiling point because it is made up of strong covalent bonds. Okay, there are no weak forces of attraction here. So in diamond, each carbon forms 4 covalent bonds with other carbon atoms in giant covalent structures. So carbon is in group 4, it has 4 electrons in its outer shell, so it can form 4 bonds. It can share those electrons and form 4 bonds. Okay, graphite is also another example of a giant molecule, and it is again made up of carbon just like diamond, but it doesn't look the same. If we go back, you can see that there's diamond in that giant structure, in that 3D structure, and if we look at graphite, Graphite looks very different. Graphite is in layers. And it's in layers because rather than forming 4 bonds, it only forms 3 bonds. So if you like, it doesn't go backwards, it just stays flat. It doesn't have that 3D shape, which means it ends up as layers. So we've now got a spare electron in the outer shell that we didn't have with diamond because only 3 are now in bonds. 1 is spare, and they form these layers. Between these layers, you do have weak intermolecular forces of attraction, forces between the graphite molecules. Okay, so graphite has the layers can slide past each other because those weak intermolecular forces of attraction. So good to be used as lubricants. If you think of when you write with your pencil, graphite comes off in sheets and layers because you can easily overcome the weak intermolecular force of attraction between the layers of graphite. Okay. So there you can see on the diagram that's your higher tier only. Graphite has weak intermolecular force of attraction, which makes the layers sit soft and slippery because the layers can just pass over each other. Okay, so weak intermolecular force of attraction. And again, you can see a direct comparison on that slide. You've got the structure of diamond in red and the structure of graphite in gold colour with the weak binding forces in between each layer. Okay, both made up of carbon, but graphite forms 4 bonds. Diamond forms 4 bonds, graphite only forms 3 bonds. Now, this again is higher tier only. Because graphite has only formed 3 bonds, it has 1 spare electron. Electrons are negative, therefore they're charged, so they can move, and that means graphite can conduct electricity. So if you sharpen both ends of your pencil and connect them to a crocodile clips into a circuit, the electricity will travel down that graphite because the electrons are charged negative particles which will be attracted to the positive end, so will conduct electricity. Okay, so in this point you can see at the bottom, it's similar to metals in that it has delocalized electrons. Okay. Other 2 structures you need to be aware of if you're doing higher tier. Carbon can also form what we call fullerenes with different numbers of carbon atoms. So here you can see a buckyball and a nanotube. So these are great because we can use them for drug delivery. So we can put the drug inside the cage so it gets protected as it gets delivered to the part in the body we want it. It's good to be used as lubricants or catalysts because again we can use that ball design to protect the catalyst inside. And nanotubes are really light and can be used for reinforcing things like tennis rackets because they are light but still very strong. Okay, on this slide here again for higher tier only, you can see that metals conduct heat and electricity because of those delocalized electrons flowing through the structure. Okay, so conduction depends on the ability of electrons to move through the metal. So if you have an alloy, you'll have a mixture of sizes of atoms within that, and it'll make it really hard for the electrons to get round and past because there's not nice neat rows. So an alloy will have a higher resistance to that electricity. Okay, because metals then have these nice neat rows of atoms, it means that we can slide the layers over each other, which means that metals can be bent and shaped into different things. Okay, like I've just said on the previous slide, you can see here this is an alloy, different shaped atoms inside that metal. Okay, so 2 or more different metals, so you can see 2 or more different size atoms in there. And that makes it harder now for the layers to slide because it's all a bit distorted. So alloys are harder than pure metals. So if we go back, you can see with a pure metal, the layers just slide over each other. But with an alloy, they can't because those different size atoms in there. The layers can't slide. So alloys are harder than pure metals. Okay. Your specification mentions shape memory alloys. They can return to their original shape after being deformed. Okay, so dental braces, they'll be heated up, changed to a shape, and then they'll go back to their original shape and pull those teeth back in line with where they should be. Okay, the properties then of polymers. So we're talking about properties in Unit 2. The properties of polymers or plastics depend on what they're made from and the conditions under which they're made. Small references in your specification. So low density and high density polymers, so polyethane you can see here, are produced using different catalysts and reaction conditions. Okay, so the conditions they are designed in will depend on their properties. So different catalysts, different reaction conditions. Here you can see a difference between two thermosoftening and thermosetting polymers. Thermosoftening polymers on your left-hand side of your screen, they consist of individual tangled polymer chains. The word you want to use here is there are no crosslinks. If you look at thermosetting, there was what called crosslinks between them, which means that when I heat them up, they don't move, they don't melt, they just burn. So if you can think of when you heat some plastics up, they just burn and they don't melt and you can't change their shape, that's a thermosetting plastic. So if you think about if you get a takeaway, Chinese, etc., that will be in a thermosetting plastic. Otherwise, when you warmed it back up in the microwave, that plastic would just melt, which is not what you want. So that would be a thermosetting plastic. Okay. Right, nanoscience. Nanoscience then refers to things that are 1 to 100 nanometers in size. You need to be aware of that number. I've seen you be asked to recall that before in the exam. So 1 to 100 nanometers in size is what we call nanoscience. So obviously incredibly small particles. So nanoparticles show different properties to the same materials in bulk and have a high surface area to volume ratio. What that sentence is saying is that nanoparticles are incredibly small, and because they're really small, they have a bigger surface area on the outside to what's on the inside, their volume. We have a pretty rubbish. We have not a very big surface compared to how much is inside as our volume. Okay, and because of that, they can be really, really useful products. So nanoparticles might be used as a really good sun cream, which soaks in and we can't see it because it's smaller than the wavelength of light. So you don't have big white blotches all over your face when you put your sun cream on. So makeups might be as well very desirable to be nanoparticle size because they give the coverage, but you can't see it as clearly. We might make nanobots to go inside the body and do very small operations, okay, or skin creams that go really deep down inside the layers and prevent wrinkles, etc. as well. So nanoparticles have got a huge future in terms of technology. Okay, this is Unit 3. This is where all of your calculations are going to come in. It's not as hard as it looks, so please bear with me. And again, I'll upload some practice stuff as well for you to have a look at, but it's not too challenging. You can do this, just make sure you've got your calculator. So reminder, this is on your periodic table, this exact little bit here. So you've got your chemical symbol with the He for helium, and you've got a number, 2 numbers either side. You've got your top number, which is your mass number. That's what's inside the nucleus, so your protons and your neutrons. And then your atomic number is 2, which is your protons and your electrons. So in this case, there are 2 protons, 2 electrons, and 2 neutrons. Okay, please remember that the relative masses, so protons and neutrons both have a relative mass of 1, and an electron you would just write very small, very, very small. The total number of protons and neutrons is called its mass number, like we just said on the previous slide. Okay, sometimes we find atoms which have different numbers of neutrons, those things inside the atom. Because they have the same numbers of protons and electrons, they're still the same type of atom, but they're different versions. These are called isotopes. The thing on your periodic table is the most common form. So hydrogen, there are 3 forms of hydrogen, but you'll only have seen 1 on your periodic table because that's the most common form that we come across. So an isotope is the same atom but a different number of neutrons, because neutrons, the way to remember is neutrons have no charge at all, so they don't affect anything, they just make it slightly heavier. Okay, the relative atomic mass of an element then compares the mass of atoms with carbon-12. Don't worry too much about this. All you need to know is that on your periodic table you will need to use the atomic mass in calculations, and we'll go through and explain how we do that. So if you're asked to find the relative formula mass, this is such an easy question, so please don't ignore it. Okay, it can be worth 2, maybe 3 marks depending on what they provide you. So if you look at this question, it looks quite complicated to start off with, but it's actually very straightforward. So they've given you a formula, C10H15NO. You've never been shown that before. Okay, we would never need to show it before, but it's quite easy to work out the question. So what relative molecular mass, or MR, would be recorded by GCMS if epihedrin was present in a blood sample taken from an athlete? Show clearly how you work out your answer. So literally all we do here is add up the masses. So there are 10 carbons. If you look back at the formula, carbon has an atomic mass of 12, as it shows you in the question. So we do 12 times 10 first. Then we add 15 hydrogens, they're 1, so 1 times 15. Then we add 1 nitrogen at 14 and 1 oxygen at 16. So we add all those numbers up, and that gives us a relative molecular mass of 165. Okay, so relative formula mass is dead easy. You just add up the atomic masses, which will be given to you in the question, but you can obviously find them on the periodic table as well. Okay, that relative formula mass then is what's called a mole. So if we go back, 1 mole of that substance would be 165 grams. Okay, so it's molecular mass, we don't put a gram after it. That's just the mass of a molecule, very, very small amount. But a mole is that number in grams. So if you add up the molecular mass of water, it's 18. So if you think that's oxygen is 16 plus 2 hydrogens both at 1, it gives you 18. So 1 mole of water is 18 grams. Okay, same for molecular mass of calcium hydroxide is 74. 1 mole of calcium hydroxide is 74 grams. Okay, so elements and compounds can be detected and identified using instrumental methods. Okay, instrumental methods come up quite frequently in the exam, so just be aware of what they are. They just allow us to find things, so we can use them for forensic science, etc. If we find a chemical and we're trying to work out what it is, or if you've seen the police airport scanner sort of type programs and they're looking for drug testing in suitcases, they can put any sort of powder they might find through a machine and find out if that is drugs or not. So they're very accurate, very sensitive and rapid. 3 important words to remember if you're asked to give advantages of instrumental methods. So accurate, sensitive and rapid. And they're particularly useful when the amount of the sample is very small. Okay. We could have used things like paper chromatography, but it's not very accurate and it's not very rapid, but you'd have probably used it in school because it's something we can do without training. So chemical analysis can be used to identify additives in food, like paper chromatography. Artificial colours can be detected and identified by paper chromatography. So this is called gas chromatography here, and what you have is gas chromatography connected to a mass spectrometer. So it's GCMS, and it's a type of instrumental method. Okay, so what happens is you send in your sample, it is vaporized, put through the column, which has small little particles which hold on to some of those things going through it. And then so it all leaves at a different time, and that's called its retention time. So its retention time will give you the information you need to decide what that chemical is, and the mass spectrometer will help you make that decision very easily. So the gas chromatography allows separation of a mixture of compounds. So like I've said on here, different substances carried by a gas travel through a column packed with a solid material at different speeds, so all become separated out. So the time taken for a single substance to travel through can be helped to identify. So different chemicals will have been passed through. Things that we know will have recorded the time it takes. When we get an unknown thing, we can put it through and see if it comes out at a time of one of the ones we know. The output then from the gas chromatography, or GC, can be linked to mass spectrometer, which can be used to identify the substances leaving the end of the column. Okay. Higher tier only part of this then, and that's only this little bit here, is the mass spectrometer can also give you what's called the relative molecular mass of each substance separated in the column. Higher tier candidates, please make sure you know that term because it often comes up. So it gives you the relative molecular mass of each substance. Okay, so the number of peaks on the output of the gas chromatograph, which is based as a graph with some lines going, looks a bit like a bar chart, shows the number of compounds present. Okay, the position of the peaks on the output indicates the retention time. So that will be read by the computer. Depending on how long it stays inside that column will depend on what it is. The key thing to remember here is whatever we're putting in is vaporized, turned into a gas, sent through that coil. It comes out at different times, so it separates it all out, and the time it comes out will tell us what it is. Okay, on to a bit more of the calculation. Again, an easy question. The majority of you will be able to calculate a percentage. If I gave you a mark on a test, you'd be able to work out what percentage you got. And it's exactly the same here. So the percentage of an element in a compound can be calculated from the relative formula mass of the element in the formula and the relative formula mass of the compound. Let's just put that into practice. So here we've got another drug, amphetamine. It's got the formula C9H13N. It's given you the relative molecular mass is 135. Calculate the percentage by mass of nitrogen in amphetamine. So you've got to imagine that C9H13N is your 100%. That's the total amount. Okay, so think about the number of marks you could have got. So in this case, it's 135. And we want to find how much of that 135 is actually nitrogen. So there's only one atom of nitrogen there, it's just N. So we do 14 divided by 135, so the total amount, and times by 100, which gives us 10.37%. Okay, so we'd write that in the bottom there, 10.37%, and we'd get 2 marks for doing that. Okay, again, please show you working out. Right, this empirical formula now is a nice question to get if you can use SMADR, but it's higher tier only. So those of you doing foundation paper, you can skip past this bit. So the empirical form of a compound can be calculated from the masses or percentages of the elements in a compound. So chlorine reacts with hot sodium hydroxide solution. A sample of a compound formed in the reaction was found to contain 10.8 grams of sodium, 16.17 grams of chlorine, and 22.5 grams of oxygen atoms. Calculate the empirical formula. Okay, so you need to use what we call SMADR. SMADR is an acronym to help remember the order of what you're going to do in the question. So S stands for symbol. The first thing we do is write out the symbols in the order they have appeared in the question. So we've got sodium, chlorine, oxygen. M stands for mass. 10.8 for sodium, 16.7 for chlorine, and 22.5 for oxygen. See, I've kept it neat here. Please do this in the exam so the examiner can see clearly what you're doing. Then we go to A. A stands for atomic mass, so check your periodic table. Na is 23. Chlorine is 35.5 and O or oxygen is 16. Then we are going to do divide. D stands for divide. And you're going to divide as it is shown in that list. So the first number divided by the second number. For sodium, 10.8 divided by 23 gives 0.47. 35.5, for chlorine, 16.7 divided by 35.5 again gives us 0.47, and then oxygen, 22.5 divided by 16 gives us 1.41. So we've now got our divisions, but we're trying to find a ratio. So an empirical formula is the smallest ratio of these atoms together. So I need one of these numbers to become 1, so I can have a ratio to it. So what I'm going to do for A now is answer divided by the smallest. So the first two are going to become 1. The smallest number in the row above, if I go back, the smallest number here is 0.47 and the largest number is 1.41. So I'm going to divide everything by 0.47, which you can see there in that line. Okay, which gives us the sodium and chlorine come out as 1 and oxygen comes out as 3. So we can now, R stands for ratio. So we now got our sodium, chlorine and our oxygen. So it's Na is 1, chlorine is 1 and oxygen is 3. So our formula is NaClO3. Okay, so if you structure it like that, empirical formula becomes one of the easiest questions you will do and is worth a good 5 marks, which goes a long way to securing your grade. Okay, please check this because last year it didn't come up, so I imagine it will come up this year. Okay, this again then is looking at how much. So silicon can be made by heating a mixture of sand with magnesium powder. The equation is shown below. Calculate the mass of silicon dioxide needed to make 1 gram of silicon. So we're just looking at the 2 things we're asked to do. Ignore the rest of the equation. It's told us to calculate the mass of silicon dioxide, so we've got SiO2 there, from 1 to make 1 gram of silicon. So we just need silicon on the other side. We're ignoring the things with Mg and MgO in. Right, underneath silicon dioxide, what we're going to do is add up the atomic masses because that's all we've got to compare. I want to know how much I need. So silicon is 28 plus 16 times 2 for oxygen, which makes 60. Silicon is 28. So again, keeping it in nice neat columns. So that's saying that 60 grams would make 28 grams. Okay, but we don't want that. We want 1 gram. So we're going to divide that, okay, by 28 to get 1. So we're going to also divide 60 by 28, and that would give us 2.14 grams. Okay, so if we wanted 1 gram, we would need 2.14 grams of silicon dioxide. Right, on to the end of this chapter now. Even though no atoms are gained or lost in the chemical reaction, it's not always possible to obtain the calculated amount. So like we just said, that I would have used 2.14 grams of silicon dioxide to get 1 gram of silicon. We don't always get that, and you need to know why. So remember a couple of these, please. For one reason, it may be reversible, so it might not go to completion. So it might keep swapping back on itself. We may lose some of the products as we're doing it, so we might get it stuck, for example, in a filter paper. And we might also have some of the reactants may react in ways different from how we expect it, so we might not be able to predict it properly. Okay, so there are 3 good reasons to why we don't always get the calculated amount of product. Okay, if we don't, then we're going to calculate percentage yield, and higher tier people, you need to know how to do that. So here we've got the expected maximum mass of ammonia produced by the Haber process can be calculated. In one process, the maximum mass of ammonia should be 80 kilograms. The actual mass of ammonia was 12 kilograms. Calculate the percentage yield. So it would be 12 divided by 80. So what we got divided by what we should have got times by 100. And that gives us 15%. Okay, so in some chemical reactions, the products of the reaction can react to produce the original reactants. Such reactions are called reversible. So you can see here, they can swap backwards and forwards as you go along. Right, on to Unit 4, rates and energy. Nice easy topic, but key thing to remember here is the word collide. Right, the rate of a chemical reaction can be found by measuring the amount of a reactant used or the amount of a product. So rate of reaction is the amount of reactant used divided by time, or the amount of product formed divided by time. Right, chemical reactions can occur when particles collide. You've got to remember that term collide, so important. And they have to collide with sufficient energy. So one way of increasing energy, for example, would be to increase temperature, because they'd move faster and hit each other harder and react. The minimum amount of energy they must have is called activation energy. So you need to know some ways in which we can speed up the rate of reaction. Increasing the temperature then increases the speed of the reacting particles, because they collide more frequently, more energetic. So please, when you get a question like this, go through step by step. So increase temperature, increase kinetic energy, increase chance of collision, more frequently, increases the rate of reaction. Do it step by step. Again, increasing the pressure will increase the chance of a collision. So again, here you can see in 2 diagrams, by pushing that lid down, we've given it less space, so we've increased the pressure, which makes it more likely for a collision and will increase the rate of a reaction. Increasing concentration increases the rate of reaction, because again, it increases the chance of collision. Please, please, please don't increase the volume. Increasing volume just increases more of it. It doesn't make it any more likely to collide, but increasing the concentration does. Think about having a pint of squash and then 2 pints of the same squash. Doesn't make it any more concentrated. But if you have 1 pint of squash and add more cordial to it and make it stronger, that makes it more concentrated. So again, you can see here, with a low concentration, we have very few collisions because they're less likely to bang into each other. With a high concentration, we have a lot more collisions and therefore increase the rate of reaction. So if you're talking about rates of reaction, you need to try and use the word collisions and frequently. Right, increasing the surface area increases the frequency of collision and increases the rate of reaction. This is really important that you get this right. On the right hand side, you can see a large square, and you can see that those little red dots, whatever those atoms are, can only collide with the outside. But if we break that square into smaller pieces, in this case on the left hand side, those red dots can now collide with atoms all over that, all on the outside and the inside of that square. So if we want to increase the surface area, we make the pieces smaller. And that's the bit to get your head around. Okay, so increase the surface area, we make the pieces smaller. Imagine a big lump of Play-Doh and then making lots and lots of small balls from that one big one. Okay, again, you'd have more surfaces for that reaction to happen. Right, and finally, you need to know that catalysts also increase the rate of reaction. The key thing here to remember, though, is that catalysts increase the rate of reaction but do not get used up themselves. Very important, because then the industry don't have to keep paying for them over and over again. So they increase the rate of reaction but are not used up themselves. You also need to be aware that they do that because they lower the amount of activation energy needed for the reaction to happen. So they make sure that the reaction will happen at a lower energy. Okay, and catalysts are important in increasing the rates of chemical reactions used in industrial processes to reduce cost. Because if I don't have to heat my reaction up as hot, I'm saving money. So if I buy a catalyst which I can reuse over and over again, and I can keep my temperature quite low, I don't need to give it much energy, then I'm going to save money in the long run. Okay. And finally, from this last bit of chapter 4, you need to know the terms exothermic and endothermic. So when chemical reactions occur, energy is transferred to or from the surroundings. So an exothermic reaction, so think exit, is one that transfers energy to the surroundings. So exothermic reactions would be combustion, so fire because it gets really hot, hand warmers, or these sort of coffee cans which warmed up the coffee. So any reaction that gives out heat is exothermic. An endothermic reaction would be like the ice packs you can buy. When you snap them, they go cold. They take in energy. Okay, so they make things go colder. So endothermic reactions include thermal decomposition and ice packs. If a reversible reaction is exothermic in one way, it has to be endothermic the other way, because if one way it would give out heat, to send it back, it's got to take that heat back in again. So again, if you get given a reversible reaction and get told one way it's exothermic, it must be endothermic the other way round. Okay, and finally, last chapter now, salts and electrolysis. Okay, please make sure you know your state symbols: solid, liquid, gas, and aqueous, AQ, just means aqueous or with water. Okay, soluble salts then. This is a bit tricky bit in C5. Please make sure you've gone over this. Soluble salts can be made from acids by reacting them with metals. So not all metals are suitable. Some are too reactive and others are not reactive enough. We can also make soluble salts with insoluble bases. So bases added to the acid until no more will react with and the excess solid is filtered off. So in this diagram you can see here that you mix it together and then filter it, and you can leave any unreacted base in the filter paper, and at the bottom you've got your soluble salt. And also you can make it with alkalis, which is basically neutralization. So an indicator can be used to show when an acid and alkali have completely reacted to produce a salt solution. Often used as a method question, so please just go over it briefly and have a little practice go before the exam. Here you can see we've made a salt solution. So number 1, we might have mixed an acid and alkali together, for example in neutralization. We heat it up to get it all dissolved. So in number 2 you can see there you've got less and less crystals, you're getting them dissolved. Then we filter and we put that into an evaporating basin. And then in number 4, all we've done is heat it, or we can leave it to evaporate naturally, or we can heat it, evaporate off the water, and we leave behind the salt that has been formed. Okay. Insoluble salts can be made by mixing appropriate solutions of ions so a precipitate is formed. And in this case, if you get a precipitate, then what you do is you pour it through and you can collect it in your filter paper. So precipitation can be used to remove unwanted ions from solutions, for example in treating water for drinking. All that's saying is, if I had some water or some waste left over from my industrial process, I could mix it with something else and make those horrible ions that I don't want go solid. I can then filter that liquid and throw away the solid particles that I shouldn't have. Metal oxides and hydroxides are bases. Soluble hydroxides are alkalis. Okay, if you want any help with that, just pause this and read through the second bit down. But metal oxides and hydroxides are called bases. Soluble hydroxides are alkalis. Effectively, they're both they're the opposite of acids. Okay, if you can remember alkalis, that's fine. But just be aware that if you see the word base, it could well be meaning alkali. So, particular salt produced in any reaction depends on the reaction between the acid and the alkali. And you need to be able to name salts produced. And again, you can see it here. If you use hydrochloric acid, you're going to make something chloride. If you use something sulfuric acid, you're going to get something sulfate being produced. If you use nitric acid, then you'll make something nitrate. Okay, so on the top line you can see sodium hydroxide reacts with hydrochloric acid and makes sodium chloride. Copper oxide reacts with hydrochloric acid to make copper chloride. Sodium hydroxide reacts with sulfuric acid to make sodium sulfate. And zinc oxide reacts with sulfuric acid to make zinc sulfate. Okay, so please be ready to name some of those salts. Ammonia then dissolves in water to produce an alkaline solution, and it's used to make ammonium salts. Ammonium salts are used in fertilizers because they help plants grow because it contains loads of nitrogen. Okay, so that's just an example of a salt and its use in the real world. Okay, acids and alkalis then. Acids contain hydrogen ions and alkalis contain OH- ions or hydroxide ions. Again, you need to know the difference between those two, please. So acids are hydrogen ions and alkalis OH- ions. And the pH scale is basically a measure of how much hydrogen or OH- ions it's got in it. So 0 or 1 will have loads and loads of hydrogen ions, and something at pH 14 will have loads of OH- ions. It'll be a very strong alkaline solution. So in neutralization reactions, hydrogen ions react with hydroxide ions to make water, and this reaction can be represented by the equation shown below. Right, on to going back to the beginning, then we talked about ionic substances. We talked about if they were dissolved in water, the ions could move around and it could conduct electricity. So the final part of C2 you need to be aware of is electrolysis. And there's a very simple diagram here. So we've got a battery pack, so we've got a positive and negative end, and you can see the wires going into the liquid, and you can see the positive and negative ions in solution moving. The negatives are going to the positive and the positives are going to the negative. So passing an electric current through the ionic substances make those ions move from one way to another, and that's called electrolysis, and the liquid is called the electrolyte. So if you look at the diagram, you can see on the positive side you've got all the negative electrons, and on the negative side you've got all the positive electrons. So during electrolysis, positively charged ions go to the negative electrode and negatively charged ions go to the positive electrode. That's the basis of electrolysis. You can also use it to electroplate objects. So for example, here you can see that rather than having an electrode, they've got a spoon, so it gets plated in silver in that solution. Okay. Again, worth remembering if you can, although the main bit is positive goes to negative, negative goes to positive, but if you can remember these words as well, at the negative electrode, anything that's positive gains that electron back. So if you think about it, the negative ion going in this diagram here is Na+. When it goes there, it wants to go back into a sodium atom, and it's currently a sodium ion. So what did we do at the very beginning to make it go Na+? We gave away an electron and it went positive. So if we give it back, it will go back to being Na. If we look on the other side with chlorine being negative, to get that to be negative, we have to give it an electron. So to go back to being a chlorine atom, we have to take that one away. So if you look at just above it, you can see the E- or the electron going up the anode, up towards the battery, and then back down the cathode towards the sodium. So if they lose electrons like chlorine has, we can say they've been oxidized. And if they gain electrons like sodium has, it's called reduction. So if you remember oil rig, oxidation is loss of electrons and reduction is gain of electrons. It might just help you score a few extra marks if you get a 6 mark on electrolysis. If there is a mixture of ions then, the products formed depend on the reactivity of the element involved. The key one here is going to be using brine or sodium chloride solution. If you have a sodium chloride solution or brine, you've got sodium, you've got chlorine, and you've got solution, or in other words, water. So you've got hydrogen and oxygen as well. So the rule here is that the most reactive will stay in and kick out the least reactive. So the two, if you're doing brine, the two positive atoms you've got, if you look at the diagram at the top, you've got Na plus and you've got H plus that will both want to go to the negative side. In this case, hydrogen will be given off because that's the least reactive, and the most reactive, sodium, will stay in solution and kick off the hydrogen as gas. Chlorine will be given off at the positive because that's negative, and the OH minus will stay in the water, in the solution. And then what will happen is the Na plus and the OH minus will go together to form sodium hydroxide. So if you get a question on electrolysis of brine, they actually make three products. It makes hydrogen, it makes chlorine, and it makes sodium hydroxide. Okay, right, higher tier people, you need to know about half equations. So when it goes to the electrode, like we've told you, that it will gain or lose electrons to go back to being an atom again. So in this case here, you can see that positive metal ions will go to the negative electrode and they will gain electrons to form neutral metal atoms. So lead is Pb2+, we need to give it back 2 electrons to go back to being Pb. Al3+, we need to give it back 3 electrons to go back to being Al. And if you have negative things, you want to take those electrons away. So here we can see we've got 2 Br minus. We want it to go back to Br2, so 2 atoms and 2 negative electrons, and the same pattern with chlorine. Okay, so please practice half equations. If you're not too sure, look those up and have a little practice, particularly if you're doing higher tier. They will not appear on the foundation tier. A couple of specific examples of electrolysis you need to be aware of that look slightly different. If you look at the diagram here for aluminium, you'll see that the 2 electrodes at the top have both got positive dots on them, and the negative electrode is actually around the outside. So aluminium is separated from its oxide in electrolysis, but you also have something else called cryolite mixed in with it. Cryolite lowers the temperature at which it will turn into a liquid, so it saves me money again if I can lower that temperature. If you imagine you've got aluminium, so things in your drink cans, and I've got to make that liquid before I can separate it, I'm going to have to get it really, really hot, which is going to cost me a lot of money. So if I add cryolite, it will save me money in the long run. So what I do here is make it into a liquid. The aluminium, which is positive, will be attracted to the negative, so will sink to the bottom and come off through that gap. And I can collect all of that positive aluminium. Then the other thing that we produce is oxygen. Oxygen is O2 minus, so it will be attracted to the positive electrode. But in this case, the electrode is made out of carbon, so the oxygen reacts with the carbon and forms carbon dioxide, which is given off at that electrode. Okay, we've talked about brine and we won't do that. Just remember that sodium hydroxide is used for soap and chlorine is used in making bleach and plastic. So we do separate brine for a reason, because the sodium hydroxide that's left in the bottom we can use to put in production of soap, and chlorine for bleach and plastics. Okay, and that is the end of C2 revision.